Hello and welcome back. This is DB2 chapter 10. We are knee deep in our discussion of indexes and various aspects of indexes. Okay, so until now we have understood indexes as dense data structures. Dense data structures in the sense that any row in the underlying table is also represented in the index. The cardinality of the sequence set, the number of entries in the sequence set, is equal to the cardinality, the number of rows of the underlying table. There are situations, and very frequent situations in real database applications, that will lead us to question this density based design. And this brief video is about such a situation and the consequences of index design. Or consequences on index design, I'm sorry. And this particular situation I'm talking of is the hot versus cold rows situation that is frequently seen in real database applications or in the patterns that you see when users query data in particular tables. You will see that rows are not being treated equally. There are hot rows and cold rows. Hot rows are those rows that are requested by almost all of the queries that you've seen in the last few minutes, seconds, days. So these are rows of particular interest to your users or applications, and every second query, every other query, many queries really focus on these hot rows, and they rather disregard and leave to the side the cold rows that are still present in your tables, but that have more of an archival value. So they are there so that you can build reports or compute statistics over them, but they are not used in your day-to-day business, in the frequent query business. Only the hot rows participate in the latter queries. Okay. So the typical situation that you will see is that the lion's share, that the largest part of the rows stored in your tables are indeed cold. Your application has been running for some time. You have acquired all cool of interesting data that once has been hot, but now has turned cold because it's days old or whatever the time frame of your application is, and just not that interesting currently. That would be one such situation, an orders table. An orders table that is tracking which orders are currently being open and when they have been fulfilled and thus shipped to the customer, for example. Okay, so of course there would be order IDs and all kinds of interesting data that we would query for and index for in our tables. But there's also the fulfilled field, and this is indicative of the hotness or the coldness of our queries. So some of these rows have indeed a fulfilled entry of null, meaning that they have not been fulfilled. Yeah? These orders are still open. We have to work on them. Our engineers, our workers are querying details of these particular orders all the time because they are currently being worked on. Okay, so this would be the hot subset of the data. The rest below here, this would probably be the colder subset because these orders have already been fulfilled. We have shipped the stuff already to our customers, and engineers are not that interested in this particular type of data anymore. Okay, so that would be the hot and cold situation in our table orders. All right. We could now perform queries over this table, and we could also index this particular table to support our predicates. But if we build that index on these particular columns that will probably be interesting to our workers, then this will lead to a distribution of the hot row set all over the indexes. Because the fulfilled column is not the indexing criterion. The fulfilled rows, the not fulfilled rows, the hot rows, they will be spread all over the indexes that we have built. And that's a pity, because this is exactly the subset of rows that is queried so often. It would be very beneficial if we could have a focused index that is only concerned with the hot rows. Okay, luckily we can formulate a simple predicate. In this case, a predicate on the fulfilled column that would simply check, well, is that fulfilled entry still null? If so, you are a hot row, okay, and you should perceive particular indexing support. If your fulfilled column is not null, then you're considered archival, and we would rather don't have you in our present indexes. You would just add to the size of the indexes, and you would be of less value to our current queries. And all of these considerations lead to the construct that you've already seen here on the top of the slide, the so-called partial indexes, which are not dense and not represent the entire contents of their underlying tables. Okay, so indeed, many database systems, many relational database systems and their B+Tree modules, they support the construction of partial indexes that cover a particular hot row set of the table only. Only those rows of the tables will be indexed, will be present in the index. As you can see, this would just be the normal create index statement, could even be a composite index, okay. But we would additionally specify a predicate, this predicate CP here, which would identify P of CP, which would identify the hot rows. Any row that could qualify regarding this particular predicate would be considered hot and would be present in the index. Only those rows. This, of course, will lead to a smaller index. That's our hope. Okay, so the index will be smaller, it will be focused. Only the hot rows will be present in the index, and we will benefit from that, because when we scan this index sequence set, we will only see hot data. Okay. Of course, once we update a row and change its CP column value, so that the column that decides the hotness of this particular row, then of course an update on the CP column may move a particular hot row out of the index into the archival subset, or rows may become hot again and move from the archival subset into the index. So an update on the CP column will lead to the presence or non-presence of a row in this partial index that we're building. When can such an index actually be used to support a particular query? When does a partial index match a query queue? And the answer is below here. Whenever we process a query over a table T, of course that must be the same table T that we have built our indexes over. Okay. Whenever we process such a query and its predicate, here's the query predicate, its predicate implies P. So if Q implies P, then the partial index can be of help to process this query. Okay. So a row that would qualify regarding Q also satisfies P, and thus will be present in the index. The index contains all the rows that would potentially match regarding Q. Maybe it contains more rows, but it will contain all the rows. We will not miss any hits regarding the predicate Q here. So implication, the predicate implication Q implies P. If this holds, then we can use the partial index that has been built with regard to this predicate P here. Okay. Well, this of course means that the query compiler or the query optimizer of our system has to decide the implication of two arbitrary predicates. And well, normally what you will find in such a database system is a very restricted implementation of predicate implication only. So what you will see that typical database systems will recognize trivial implications only. But the construct is still of some use. And I think we can see that if we now switch over to the terminal. Let's let's do that. Here we go, and we are over in our PostgreSQL terminal again. Okay, so let's see. We are still talking about our index table, of course, and we now have columns on indexes on the columns A, B, and C from our previous experiments in the previous videos. We will now add another index on the A column. As you can see, it will be another index on the A column, but it won't be dense, it will be partial, okay? And only hot rows or only super interesting rows will be present in this partial A index. And you see, this is our hotness criterion, okay? So any row that has a C value larger or equal to 0.5 is considered to be interesting, hot, and thus will be present in this partial index. Updates on column C that reduce the C value below 0.5 will remove that particular row from the partial index. Updates that make the C value at least 0.5 will move that particular row into the index. Okay, so I've prepared all of this already. Let's look at the current state of the table index and all its indexes. Quite the number of indexes that we have already acquired below here. This is an artifact of all of our experiments, and well, probably at some point we should question whether all of these indexes are indeed needed in our application. They lead to space usage and they lead to maintenance overhead. But for now we are okay with that, and you see that indeed the predicate is an integral part, an integral characteristic of this partial index. Okay. Well, what we were hoping for is that this partial index is more focused and indeed is smaller and contains fewer rows. And we can of course check that. We would just query the system catalog for all the heap files that are associated with our index table. We would use this pattern match predicate here. Oh, pattern match predicate. Okay, we have talked about this in a previous video. All right, and then we will check for the number of pages that all of these associated heap files, the table file, and all the indexes occupy. Should see 5 entries here. Perfect. Okay, so the largest, of course, is the base table. The indexes are all somewhat smaller. Well, the textual index is large, but our partial index is smallest. This is what we've hoped for, a really focused index that only contains rows with C value greater than 0.5. Especially if you compare it to the other full A, the dense A index, well, it's about a third of the size, right? So let's check for the real sizes here. You can see for the number of rows that are actually included in these indexes. This is what I'm doing here. So I'm looking for the number of rows in the dense index. All of the rows are in there, and in the partial index, and of course only those with the C value larger than 0.5 or equal 0.5 will be present there. Okay, and let's also compare that with the page sizes that we've just seen. So the full index 2,745 pages. The smaller the partial index 922. So if we look at the percentages that we see here, then indeed, oh, okay, so about 1/3 of the rows are considered hot, all right, and the index constructed for this for these hot subset in rows is indeed only 1/3 of the size of the dense of the full index. So indeed, the space savings that we've hoped for, they are indeed to be seen here. That's perfect. So now let's see whether this index is actually cleverly being used and whether it can help in speeding up queries on our index table. So if we look at such a query now, we would have to ask ourselves whether our partial A index can indeed help us. And if we are looking at the predicate on the column C that determines hotness, then you probably recall from the previous slide that predicate implication makes all the difference here. So if this predicate implies the hotness predicate of our partial index, then we could use that partial index to to process this query. Of course, all the other parts of the predicate have to indicate that this index can help at all. But this is a range predicate on the A column. We have built a partial A B+Tree, so this could be evaluated with this B+Tree on the A column, given that, well, that this restriction implies the hotness condition, and indeed it's like that. Any row that has a C value larger than 0.6 indeed has a C value that is larger than 0.5. Trivial implication here, PostgreSQL will detect that and will use the partial index. Let's hope so. All right, let's see. Yes, okay, so indeed the partial index has been used in an index scan even. Okay, so as you can see, the conjunctive predicate here has been split in two parts. It has been split into the index range condition, because our partial A index still is an A B+Tree on the A column. So this would be the index condition. But there would be some residual predicate evaluation work to be done, because the index partial A index will contain all the rows with a C value larger than 0.5. Some of them have to be removed. Some of them have to be removed because we are more picky here. We are more picky in the real query. And indeed, you can see that part, this residual part, interpreted predicate part, is still to be found here as an extra filter. And indeed, it finds some rows that were present in the partial index but had to be removed. Okay, so partial index has been used. All right, next query. This should be an even better fit, because now the implication is perfect. So we are really looking for all the hot rows. Only those are present in the partial index anyway. This is unchanged. So indeed, an index on the A column should help here. That's fine. And in this case, there should be no residual predicate work to be done, because this is already implied by the index anyway. Any row that we find in the index implicitly fulfills this part of the predicate. We should not see it considered separately in the resulting plan. So let's see that. Okay, yes, there you go. Okay, so all we've left is the index range condition. We need that, of course, but this predicate is already implied because we are looking at this index which considers these rows only anyway. All right, and now, of course, for an example where this implication fails, okay, this is still a predicate that looks for A column values, so that's interesting for any index that can support ranges on the A column. Okay, but as you can see, this predicate does not imply the presence of the row in the partial index. If we would use the partial index here, we would probably miss some rows that could satisfy this particular predicate but are not present in the partial index. So it's not safe to use the partial index here. No predicate implication. And if we evaluate this query, then we should indeed see that, well, index usage is going on, but we may not use the smaller, more compact partial index. We are using the full index to evaluate this index range condition, and there's some residual work to be done regarding the predicate on the C column. Okay, so this is partial indexes, which can be super efficient if these indexes are indeed very small. And I invite you, maybe later on in your professional career, to investigate the behavior of your application and your users. You will very often see that indeed particular rows of particular interest in a given frame of time, these rows are considered hot. All right, and well, it may make sense to then index them in a partial index. Okay, so much for that. That's already the end of the discussion of partial indexes. I think there's 2 or 3 more videos ahead regarding indexing content before we can call it a day here. But I think every minute spent on index technology is worth it. It really is the core at the heart of relational database systems. Let's spend some more time on these indexes in the upcoming videos. See you then.